You clicked because you saw a headline claiming a single computer can run a trillion parameter model at over 4 tokens per second using Intel Optane Persistent Memory. That sounds like the ultimate hack for any engineer trying to build large language models on a budget. The real problem is that this claim contradicts the fundamental physics of how these systems actually work. By the end of this video, you will understand exactly why memory bandwidth matters more than total capacity, and why that marketing promise is an illusion that could cost you weeks of debugging time. Let us start by looking at what Intel Optane Persistent Memory actually is. It is a type of non-volatile memory that sits between your standard random access memory and your solid-state drives. The marketing pitch is compelling because it offers byte addressability and persistence, meaning you can access individual bytes like RAM, but the data stays there even when the power is cut. This sounds perfect for storing massive models that simply do not fit into standard system memory. The idea is that you can load a trillion parameter model directly into this persistent memory and run it at speeds that rival traditional high-end setups. However, the performance numbers tell a different story. When we look at the raw specifications, the read bandwidth of a single Optane module is approximately 6.6 gigabytes per second. In contrast, a standard DDR5 memory module can push data at speeds that are an order of magnitude higher. This difference in throughput is the critical factor that determines how fast a model can generate tokens. Inference speed for large language models is strictly bound by memory bandwidth. The system must stream the weights of the model to the processor as fast as possible to calculate the next token. If the memory cannot feed the processor fast enough, the processor sits idle waiting for data. The latency numbers are equally damning for high-speed inference. Optane has a latency of roughly 346 nanoseconds. Standard DDR5 DRAM operates at around 35 nanoseconds. This means Optane is roughly 10 times slower to respond to a request than standard memory. In the context of running a large language model, latency is the enemy. The attention mechanisms in these models require rapid access to data repeatedly. When the system has to wait 10 times longer for every data access, the entire decoding process grinds to a halt. The compute-intensive parts of the model, such as the key-value cache and activations, cannot keep up with the slow data delivery. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Here is the thing that the hype often misses. The claim of running a trillion parameter model at 4 tokens per second relies on a specific memory tiering architecture. In this setup, the model weights reside in the persistent memory, but the active computations are bottlenecked by the much slower data paths. The system attempts to hide the latency by prefetching data, but the sheer volume of data required for a trillion parameter model overwhelms the available bandwidth. Without a massive buffer of fast DDR5 or high bandwidth memory to absorb the high bandwidth demands of the active layers, the system becomes EO bound. It is forced to wait for the slow storage to deliver data, making it significantly slower than a smaller model running entirely on fast DRAM. Consider how data moves through a large language model during inference. Every time the model generates a new token, it must read the entire set of weights. For a trillion parameter model, this is a massive amount of data. If that data is sitting in Optane, the system has to traverse that 10 times slower latency path for every single calculation path for every single calculation. The result is a severe bottleneck that prevents the rapid parameter streaming required for high token generation rates. You might have the capacity to store the model, but you do not have the speed to run it. The physical constraints of the hardware simply do not allow for the raw throughput needed to sustain 4 tokens per second. Now consider the specific workloads where Optane actually shines. It excels in database workloads where the access patterns are different. Applications like RocksDB can see performance gains by using Optane because they can optimize for persistence and reduce I/O latency compared to traditional SSDs. These gains rely on specific software tuning and careful data placement. The technology allows for 2 times performance gains in optimized persistent applications, but these gains come from reducing the time it takes to write data to disk, not from increasing the speed of random reads. This optimization does not translate to the raw throughput demands of large language model inference. The engineering effort required to make this work is often overlooked. Successful large-scale deployments on Optane require custom data movement logic using libraries like the Persistent Memory Development Kit. You must write code that prefetches weights and manages data locality with extreme precision. Naive implementations suffer from what we call the latency wall. Without that massive engineering overhead, the system will throttle performance rather than accelerate it. The magic narrative overlooks the fact that you cannot simply plug in this memory and expect the same speed as standard RAM. This brings us to the core insight that changes how you should approach hardware selection. The confusion often stems from conflating storage capacity with execution speed. You can store a trillion parameter model in Optane, but that does not mean you can run it efficiently. The primary constraint for tokens per second is memory bandwidth, not total memory capacity. A system with less total memory but faster bandwidth will almost always outperform a system with massive capacity but slow bandwidth when running inference. The illusion of speed comes from the fact that you can load the model, but the actual generation rate drops precipitously as the working set exceeds the fast cache. The evidence challenges the angle that Optane is a viable substitute for DRAM in high-speed inference. Without massive parallelization or specialized hardware acceleration, the architecture will likely throttle performance. The claim of 4 tokens per second is an illusion of data placement rather than raw Optane speed. It suggests that the model weights are in persistent memory while the compute-intensive parts are bottlenecked by DDR5 bandwidth, creating a mismatch that slows everything down. For a junior engineer, this means you need to prioritize bandwidth and latency over raw capacity when designing inference systems. The gap between marketing headlines and the reality of inference speed bottlenecks is vast. You cannot replace expensive GPU VRAM or fast system RAM with cheaper persistent memory and expect the same performance. The physics of the hardware dictate the limits. While Optane has its place in specific database workloads, it is not the magic solution for running massive language models at high speeds. Understanding this distinction saves you from building systems that look good on paper but fail in production. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.